Welcome to Introduction to Geology. I'm your host, Dr. William Patterson. Today we're going to be talking about igneous rocks, solids from melts. This is part 2 of 2, in which we'll talk about magmatic differentiation and plate tectonics and igneous processes. Magmatic differentiation is a process by which rocks of varying composition can arise from a uniform parent magma.
Want to cook?
Here we have a diagram we saw recently of magma chamber A and magma chamber B. We'll start out with magma chamber A here. This is made of partial melting of country rock. This is the surrounding rock. It's being melted and accumulating with a magma of a particular composition in this chamber. Cooling causes minerals to crystallize and settle. So as these minerals form, they're taking certain aspects of this magma chemistry, removing it and dropping it or plating it out as a pile of minerals at the bottom of the chamber, changing the chemistry of the remaining magma. Now, in the instance of magma chamber B breaking through, this is a basaltic magma chamber, so it has a much more mafic composition. So now we're juicing up magma chamber A with an infusion of ferromagnesian ions. Magma chamber A now has a new chemistry. We're still adding some of this partial melted country rock as well. Much more complicated magma chamber than what existed previously. Mixing results in andesitic magma. So this is an intermediate magma. It's going to go from, say, a felsic composition to an andesitic composition here. So the color transition will be from a lighter color to a grayer or intermediate color material. Crystals are again going to accumulate on the sides, the bottom, and the roof of the chamber, in this case due to turbulence. So as the mixing occurs, these minerals are going to crystallize and then stick to one another around the magma chamber, the boundaries of the magma chamber. Subsequent minerals are going to be of more exotic compositions than what we saw in the original magma chamber composed of molten country rock. Now, igneous intrusions, bodies of magma that solidify below the Earth's surface, have a number of different forms and characteristics. So we'll talk about those here. This diagram pretty much covers all the bases. Discordant intrusions include plutons and batholiths. Batholiths being the largest form of pluton, covering at least 100 square kilometers areal extent. Stocks cut across country rock as well, ultimately perhaps forming a volcano. Dikes are discordant, cutting across country rock. Veins, likewise, will cut across country rock. Concordant intrusions, on the other hand, conform to the previously existing rock. These include laccoliths, which are lens-like or kind of an upside-down bowl shape. Sills, which are concordant versions of dikes. Sill, like a windowsill, and after relatively loose material weathers away, we may be left with a volcanic neck with radiating dikes. Our best example in North America is Shiprock in New Mexico. You can see here the radiating dike coming away from the former vent, another radiating dike here, and one off to the northeast here. A sill, as we mentioned a minute ago, runs parallel to country rock layers. This is an example from northern Wyoming, southern Montana. A thick sill has worked its way into this sedimentary sequence. Alternatively, dikes again cut across sedimentary structures. This is Yosemite Valley. It's our best example of a batholith exposed at the surface. This is the Sierra Nevada Batholith. This massive body of rock formed between 105 and 85 million years ago as the Farallon Plate was subducted underneath North America. The partial melting of the upper crust led to this felsic composition, which cooling slowly produced this granitic rock, which is very resistant to weathering. It's resistant to weathering because it forms at relatively low temperatures over very long periods of time. The resistance to weathering gives us these steep cliffs. This is the famous Dawn Wall here and Half Dome here in the distance. The only thing that was able to cut through this rock is a series of glacial events, maybe 14 in all. It attracts climbers from around the world. If you have Netflix, this is worth watching, not only for the crazy story and the crazy adventure, but for a close-up of the characteristics of this rock and why it's so good for climbing.
When you see El Capitan for the first time, it takes your breath away.
Early in the morning, there's this one panel of the wall that illuminates first, the dawn wall.
It has never been climbed until Tommy Caldwell came along. Nobody had actually considered trying it.
It's like stepping off the edge of the earth.
I guess the question here is, why are you doing this?
I was this very fragile little kid.
He didn't crawl till he was over 2.
I think my dad felt the best way to prepare this kid for the world was to toughen him up a little bit. And so he took me on all the craziest climbing walls you could ever do, and he did it with a 6-year-old. By the time I was 14 or 15, there was climbs that I could do that my dad couldn't.
Tommy became one of the best young climbers.
And then he got invited to Kyrgyzstan to rock climb. And all of a sudden, we were hostages.
After being held captive for 6 days, 4 young Americans confront the ultimate choice: to kill or be killed.
He saved our lives.
But he became a different person.
Ever since Kyrgyzstan, I just have this fire in me. This has always been my safe place, my way to deal with life. And I was looking across at the dawn wall, the last unclimbed big swath of stone. I decided maybe that could be climbed. I needed a partner.
Kevin, he was one of the best in the world. It only up about 30 feet.
But everybody else thought I was crazy.
At this point, I have no idea what I'm getting into. It's about to consume 6 years of my life.
This is a pipe dream, man. Come on.
Nothing left to do but just take a couple deep breaths.
If Tommy and Kevin can actually do this, it will be, come on, the most difficult climb ever done. And it's going to go on day after day.
Suddenly, the whole world was watching me.
And one of them stuck. It was pretty clear that that was it.
I don't want to hold you back.
Maybe this climb really was impossible. We are capable of so much more than we could ever imagine.
This image of Half Dome from the other end of the valley gives you a better perspective of the felsic nature of this igneous rock that was formed at considerable depth from a slowly cooling melt. Now, how do these bodies get emplaced? Well, rising magma wedges open and fractures overlying country rock. So the pressure from below is going to fracture this material, and it allows for the intrusion of these dike swarms. The magma is also going to melt surrounding rock and break bits of it off. These bits that break off and get incorporated into the magma body itself are known as xenoliths, or strange stones. These are going to sink into the magma and potentially melt, or be included in the magma as the original body with some reaction zone around the edges of it. So both of these are common: the total dissolving, melting of the xenolith and the preservation of the xenolith. Moving on to the influence of plate tectonics, we have a series of diagrams here we're going to focus on over the next few minutes, including ocean-ocean convergence, spreading centers, hot spots, and ocean-continent convergence. These are the magma factories: spreading centers, subduction zones, and mantle plumes. Ocean-ocean convergence. This is when 2 oceanic plates come together. One is going to be subducted beneath the other because the Earth's surface doesn't change in size. So creating new crust means you have to get rid of some old crust. The result is we have an island arc volcano sitting above the subduction zone, and the subduction zone is driving down wet sediment where the presence of water is going to reduce the melting temperature of the surrounding material, generating a melt. This magma chamber is going to form at a lower temperature than would be possible if there were no water present. Our example here is an island arc volcano in Indonesia. These are some of the most explosive volcanoes on Earth. Alternatively, in a spreading situation, such as in the mid-Atlantic, we have basaltic intrusives and basaltic extrusives forming as one ocean plate. The European plate moves away from the North American plate. This is going to reduce pressure, and that reduction in pressure is going to enable melting. again at a lower temperature. So this is going to encourage the emplacement of magma in this low pressure zone. And this is a rare instance in Iceland where we can see the mid-ocean ridge at the Earth's surface. You can get out and walk around in here. There are waterfalls that pour into here. You can do scuba diving. It's a pretty cool place. So these magma factories can be spreading centers, subduction zones, or mantle plumes. Now hotspots are a different situation. In this instance, we have a mantle plume which forms the hotspot, rising through the Earth's crust to form a volcano at the surface as seen here. Now either the plume itself moves or the Earth's crust moves over the plume. Regardless, it doesn't matter.
What's the difference?
There is relative movement, one versus the other. Hawaii is our best example of hotspot volcanism on oceanic crust. These are relatively quiescent eruptions because the magma is low in silica. It flows very easily. In the case of continent-continent collision or continent-continent convergence, mafic to intermediate intrusives and mafic to intermediate extrusives are going to result. So in this instance, we have oceanic crust being subducted beneath continental crust. This continental lithosphere is more buoyant than the oceanic lithosphere, so it literally floats on top. Subduction of wet sediment is going to reduce the melting temperature, encouraging magma formation. And because of this intermediate composition, it's going to be relatively viscous compared to the magma we see in Hawaii. Therefore, this volcanism is much more explosive. This is Mount Rainier in Washington, near Seattle. It is due to go off at some time. We don't know when, but it will be spectacular. This is Kuhn checking out the volcanic activity on Mount Rainier. Where does this magma come from? It comes from decompression, melting, and spreading centers. As the pressure is reduced, rock melts. You don't need to do anything else. You don't need to change the temperature, just reduce the pressure and rock could melt. So here we have hot mantle rising, decompressing, and melting, generating a large magma chamber. Within this magma chamber, we have crystallization of olivine. This olivine is going to fall to the bottom of the magma chamber, forming what's called a peridotite layer. Peridotite, again, is just olivine with some pyroxene. Above that, we have gabbro, and above that, we have sheeted dikes in basalt. So this is a sequence of millions and billions of dikes that are forming as this ocean crust is created. Fluid-induced melting in subduction zones is another major source of magma. Again, by adding water to a material, you lower the melting point. So here we have a close-up of what's forming here at the spreading center. These are known as pillow basalts because they look like pillows. Here we have thin dikes erupting, spilling lava in the form of pillows. These dikes are going to be intruded by other dikes, forming what are known as sheeted dikes. Sediment is deposited on the spreading seafloor. The gabbro layer metamorphoses by contact with the magma. Cold seawater is going to be pulled down through these sheeted dikes where it's heated. As it's heated, it loses density and it rises, and it's rising, carrying dissolved minerals. When it reaches the seafloor here, the temperature is going to drop from 400 degrees or so to close to zero instantaneously. And the result is we get precipitation of minerals in the ocean immediately. Taking a closer look at this, we have a magma chamber in which olivine is being precipitated. These olivine crystals are going to fall to the bottom of the magma chamber, forming a peridotite layer. Peridotite is just another word for olivine. So these crystals are going to settle out and form this peridotite layer like a conveyor belt as this new crust becomes older and denser and colder. This is an example of a black smoker where you can see the hot water coming out of the sheeted dike system at 400 degrees centigrade or so, hitting the bottom water of the ocean, in this case the Atlantic, with a temperature of around 2 to 4 degrees or so. And the result is instantaneous precipitation of these sulfide minerals. White smokers are less common, yet still significant. Now, in the case of fluid-induced melting at subduction zones, we have ocean crust diving beneath ocean crust. Wet sediment that's trapped on top of this plate is going to be subject to melting, again because of its wetness. That molten material is going to rise, forming an island arc. This would be like Japan, the Philippines, the Aleutian Islands of Alaska, etc. So these oceanic sediments are going to consist of microorganisms, silts, sands, clays, lots of water that's going to be crushed, heated, and subducted. So the subducting ocean crust is going to carry this wet, messy sediment with it. Sediment is going to consist of grains, organic matter, microorganisms, and water. Ultimately, this is what comes out of the volcano as gas. Water remains trapped as the pressure and temperature increase. This is a critical point, causing the sedimentary rocks to melt at lower temperatures than they would otherwise. This water and molten sediment melt parts of the overlying plate. That results in lithospheric magma. Our example here is Toba. Lake Toba is the caldera that remains after the eruption of Mount Toba that took place around 74,000 years ago. This was such a massive eruption that it nearly caused the extinction of human beings. Human species, all of the human species that were around at that time, nearly went extinct because of this singular eruption. Unfortunately, we survived, and now look at the mess we've made.
Toga, toga, toga.